In the next couple of weeks, we will switch gear and talk about classification problems. And what is a classification problem? We have n observations. Each of them consists of p measurements or p features, and they are from two classes. So this is different from regression problems where the target we aim to predict is a numerical outcome. But in classification problems, the target we aim to predict are class labels. And for simplicity, let's assume only binary classes. And the goal is to find a classification rule which takes the p measurements as the input and outputs the class label. And here will be just two labels for binary classification problems. And we would like our prediction rule make small errors not only on the n training samples, but also on future observations. And for example, in project 3, we're going to analyze the lending club data, and the p measurements would be various features about the loan or the borrower, and you aim to predict whether a loan was in default or paid off. In sentiment analysis, which is your project 4, the p measurements would be various features about a movie review, and you aim to predict whether the movie review is positive or negative. Again, there are two classes you aim to predict. How to learn a classifier? We've gone through the following steps many times with regression. This is the typical steps for solving a supervised machine learning problem. We're going to start with collecting some training samples, xi, yi. Here, xi denotes the p-dimensional features, and yi denotes the binary response. Without loss of generality, we're going to assume the two classes are labeled as 0 or 1. Then we're going to pick a collection of functions, f, that takes p-dimensional input and outputs a binary response. For example, if we focus on linear function, then we can index every function in this function collection of functions by a parameter and theta. And then we're going to pick a loss function that measures how happy we are with our prediction fx when the true response, the observed one, is y. For example, for the 0-1 loss, if our prediction agrees with y, then the loss is 0. And will be 1, the loss will be 1 if they disagree. And the last step is optimization, and where we minimize this average loss over the n training samples, and then that will return us the optimal function f, optimal classifier. If our function is indexed by some parameter theta, and then the last step basically becomes a parameter estimation problem. We wanted to find a set of parameters. They minimize those empirical loss over the n training samples. Next, let's consider an ideal situation where we have infinite samples, or equivalently, we know how data xy are generated. Then there's really no difference between training sample or test samples because we know all the data. And then when n gets to infinity, and this loss function becomes an expectation over the loss function, where the expectation is taken with respect to the true data generating process, a joint distribution over both x and y. And that expected loss is sometimes referred to as the risk function of a classifier f. And it's reasonably to define the optimal classifier to be the function f star that minimizes the risk function. Let's assume we're going to use the 0-1 loss function, and also we are allowed to use any function f. Then what would be the optimal f star? Next, let's look at the risk function and see how we're going to find f star that minimizes this risk function. So the risk function is defined to be the expected loss function, where the expectation is over the joint distribution of x and y. Assume x and y are continuous, so the expectation is equal to a double integral of the loss function and then times the joint density function and dy and dx. Here, without loss of generality, we assume x, y are continuous, so expectation is evaluated by integral. But if it is discrete, then we just change the integral to summation. and then the density will becomes probability mass function. And then at the second line, we basically factorize the joint as a product of marginal of x, px, and then the conditional of y given x. So the product of these two is equal to the joint density and joint distribution. And then from the second line to the third line, we basically move px out of the bracket because the quantity inside bracket is an integration over y, and px has nothing to do with y. So let's move to the next slide. On the top, I just copy whatever expression I had on the previous slide. And now you're going to find out the problem of finding f that minimizes the risk and can be reduced to a series of sub-problems. All we need to do is for each x, given x, lowercase x, find what is the optimal value for an fx. It will minimize the quantity inside the bracket. The blue integral inside the bracket measures the loss of function f at a particular point x, and the outside integral basically returns us the average loss over all the x range. So if a function f that can achieve the smallest possible loss at every location x, then its average loss, basically the risk, should still be the smallest. And that's exactly what is this f star, the optimal classifier. So the optimal classifier at every location x is defined, will be assigned to a value a that minimizes that blue integral. And we can construct our f star this way, and for every x we can assign a value a that minimizes that integral. So apparently f star may not be continuous, but here we do not really care continuity at this moment. All we want to do is to find f star that minimizes the risk. So to solve f star, we just need to solve and to find optimal a that minimizes this integral. And this integral turns out to be not difficult to solve because y is just a discrete random variable taking two possible values. So on the next slide, we're going to just evaluate this expectation, which is going to become a summation. And we need to know what is the distribution of y given x. So given x, y only take two possible values. Let's denote the probability of y equal to 1 to be eta. And because this probability may vary at different x, so it is really a function of x, so eta x. And this means that given x, y follows a Bernoulli distribution with parameter eta x. So let's evaluate this and this integral. This is integral over y, and because y is discrete, it becomes a summation. So we sum over the two possible values for y. First, y is equal to 1, and then the corresponding probability is eta x. And then y is 0, and then the corresponding probability is 1 minus eta x. Okay. This sum is a function of a. A can only take two different values because our a is supposed to be the value of our classifier, the optimal classifier. So a can either be 1 or 0. So if a is 1, and because we use 0, 1 loss, so if a is 1, then loss is 0, so we get 1 minus eta x. Now if a is 0, then this we don't have this part, and the loss is eta x. Which a value will minimize this? It depends on the value of eta x. Eta x is a conditional probability, meaning it takes the value from 0 to 1. So if eta is bigger than 0.5, then which of the two numbers is going to be smaller? It's going to be this one, right? So that means if eta x is bigger than 0.5, the optimal value we should assign to f star x should be 1. In other words, if at a location x, if the conditional probability of y equal to 1 is bigger than 50%, then we should predict and predict the label to be 1. It makes sense. And if eta x is less than 0.5, then we're going to predict y to be 0. So this is the optimal classifier, and because it minimizes the risk when we use 0-1 loss. And this classifier is often called the Bayes rule, and the corresponding risk is often referred to as the Bayes risk or Bayes error, and which is what exactly you computed in coding assignment 1. We just showed that at every location x, if we use L1 loss, the optimal decision rule or optimal classifier is based on the conditional probability of y. And if the conditional probability of y equal to 1 is bigger than y equal to 0, then we're going to output 1, otherwise 0. The calculation can be easily extended to multi-class problems, where our y is going to take k different values, 1 to k, and then it's easy to show that if we use 0-1 loss, the optimal decision rule again is based on the conditional probability of y. We will predict at every location x, we will predict y to be the most, the class label has the highest probability. Before closing the introduction section, I want to introduce some jargons. Here, our classifiers are defined to be functions that can take a p-dimensional feature vector x and output 2 labels 0 or 1. So sometimes it's very intuitive to look at the x space and look at which regions fx will be 1 and which regions they will be 0. For example, in this picture where our feature space is 2-dimensional, and if we shaded the regions where the prediction is 1, then this picture will tell us a lot about the classifier f, and we really don't need to describe the functional form of f. And sometimes all we care is the so-called decision boundary, and decision boundary would be the location of x's where eta x, which is this function, is exactly equal to 0.5. In this case, the decision boundary would be the 2 circles here. Sometimes if the decision boundary is a linear function, then we would call the classifier f to be a linear classifier.